Uh, Hello, good evening to all. Can we wait 2 more minutes or we can start now? I observed that a less number of people listen. Is everyone audible?
Yes, ma'am.
Okay. Okay, we can start now. It's more than 4 minutes. Welcome you to all to the course Operations Research. Myself, Jayanagasri, PMRF Research Scholar from the Department of Mathematics and Statistics, University of Hyderabad. In this week, we cover the topics related to duality in LPP and also revised simplex method, right? So let's start the duality in LPP. What is duality in LPP and why we are tending to use the duality concept in LPP? Means uh, this discovery of duality is the fact that every linear programming problem has its associated another linear programming problem. The original one we can say that it's a primal LPP, and the latter are another LPP we can say that the dual LPP. So if we obtain a optimal solution in a primal or if we obtain a optimal solution in dual, then it is easy to uh, give the information about the other optimal solution. And more why we are using the duality means sometimes we may tend to get the solution more easier than the primal in the dual case. And we can see the conversion of primal LPP into the dual problem. How we can convert the primal LPP in the dual problem. Let us suppose that our primal problem is in the way of maximum of objective function z, that is equal to the cost coefficient c and the decision variables x, and the subject to constraints, let us suppose that in a matrix form a x, a is the constraint coefficient matrix, and x decision variable matrix is less than or equal to some b. Then and decision variables x is greater non-negative restrictions x greater than equal to 0. So in this problem, how we can convert this primal LPP into the dual? Means first you can say the steps required to conversion. That first, if we have the given problem in LP, assume that it is a primal, and if the primal is in the objective function is maximum, then here primal, and here you can see dual. In the primal case, if the objective function is in the maximization type, then in the dual, coming to the dual type, it is in the minimization type. And if the in the maximization type means the construction are less than or equal to type, and coming to the dual, all the constraints are greater than or equal to type. And also one more other things is, in the primal case, whatever the cost coefficients are involved, that becomes the, here in the cost coefficients, uh, sorry, cost coefficients that has become the RHS constants in the dual problem. RHS constants. And in the primal problem, the constraint coefficients, which are the constraint coefficients, are involved. If the column in the primal problem, that becomes the row constraints in the dual problem. Column constraints changed as row constraints in dual problem. Is it okay? And whatever, which anything I left. And how many of the decision variables involved in dual means how many of the constraints in primal, that many of the decision variables would be in dual problem. How many constraints? That many variables in dual case. So with the help of these steps, we can say that for the given this LPP problem, we can say that in the dual case, it is in the minimization type, minimum of Z that is equal to examination will be MCQ type or descriptive type. Which for the final examination, I also don't have the idea about the final examination. Let's see how it would be. So in the primal problem, it is maximization type. Coming to the dual, it is in the minimization. And here the cost coefficients would be whatever the RHS constants involved in the primal. That are the, sorry, here it is X. And subject to constraints, or here we are assuming that A as a matrix. This becomes the transpose. Why? Because we are saying that whatever the column constraints in primal becomes the row constraints in dual. So it would be the transpose. And okay, we can take another variable without any confusion as Y, and these are greater than or equal to C transpose. And Y are the variables involved in dual problem. Did you understand this conversion? Okay, let us see a problem, how to convert the primal problem into a dual. Here is a question that the dual of the given LPP is, that means asking to find the dual to the given problem. So in this type of question, first I can say you the easier way, that first we convert the given problem into the standard LPP. In the given problem, the objective function is minimum of z, that is equal to 48x1 plus 21x2, and subject to the constraints are 2x1 plus 8x2 is equal to 1. Okay, in the standard standard form of an LPP, what we do? We convert the constraints into the equations. The first one is already in the equation format. And to convert the next thing is greater than or equal to sign. So how we convert this into the equation? Anyone? So what we have to do here to convert this into the equation? I'm asking you.
I'm subtracting surplus variable now.
Okay. So let us assume x3 is the surplus variable, so that it becomes the equation. And in the second case also, it is greater than or equal to sign, so we are subtracting with another surplus variable, that is equal to 4. And here they mentioned that x1 is the non-negative variable, but x2 is an unrestricted in sign. So that whenever we have an unrestricted in sign, we have to replace the given variable into the difference of another two variables. Let us assume that x2 dash and x2 double dash are another two variables. So there is a difference between two variables we have to replace in the given question. Then we can get, okay, let's start from here. Minimum of z is equal to 48x1 plus 21. We are replacing x2 as x2 dash minus x2 double dash. And the subjective constraints becomes 2x1 plus 8x2 in the place of x2 dash minus x2 double dash, that is equal to 1. And 3x1 plus 4x2 means x2 dash minus x2 double dash. Now you write this in the matrix form. So if we write this in a matrix form, what we observe that for the constraint equations. Okay, let's start with the objective function. For the objective function, how would be the in matrix form? First is 48, 21, and for minus 21. Here x1, x2 dash, and x2 double dash. Yes, but here we had added the surplus variables. So in the objective function, the surplus variable coefficient would be 0, and the surplus variable is x3, and another surplus variable 0 into x4, right? This would be the standard form. So here we add another 0 and 0, two zeros for the two more surplus variables. So this is the column matrix and this would be the row matrix. It is the matrix representation for an objective function. And the matrix form to the subject to the constraints is 2 for x1 and 8, here say x1, x2 dash, x2 double dash, x3 and x4. So then minus 1, 0, 0. And here 3, 4, minus 1, 0. 17, 4, minus 4, sorry, here minus 4, and 0, minus 1. And the column matrix would be x1, x2 dash, x2 double dash, x3 and x4. This is equal to 1, 6, 6. Is this 6? 4. Is it so? Okay, next, to convert this into the dual problem, what we have to do now? This is the standard form representation to the given LPP. Now here our objective function is in minimization type. Then coming to the dual problem, it would be in maximization type. So maximum of z is equal to the cost coefficients would be the whatever the constants in the RHS side of the primal, that would be the cost coefficients in the dual. What these are? 1, 6, 4. And how many of the variables come to the dual problem in our problem? How many of the variables comes under dual? Anyone please respond. In this case, how many of the variables we have to take in a dual problem?
And three variables, no?
Is it so? Why it is 3
Ma'am, because there are three equations in the primal, ma'am. So
equations?
there will be three variables. Ma'am, subject to constraints. There are three constraints, so there will be three variables, ma'am, in
Oh,
dual.
okay. So how many of the constraints involved in the primal, that many of the variables comes to the dual problem. So these are the three constraints in the given problem. So we had the three variables. Let us denote those are y1 and y2, y3. Here it is the minimization type in primal. So it would, in our case, mm, okay, let's see. In our case, it converted as minimum of z, and that is equal to, in the RHS side, the coefficients, the constants are 1, 6, and 4. So it would be 1 y1 plus 6 y2 plus 4 y3. This has the, sorry, here it is maximum, because since we had minimum. So that would be the objective function. Now, what would be the constraints in our equation? We just need to transpose the given constraint matrix. That is 2, 3, 17. Please do by yourself and let me know the answer. 844 minus 1 minus 4 minus 4. Now this is our constraint matrix. Why? Because the column constraints in the primal problem would be the row constraints in the dual problem. So where the column constraints involved in primal, now I transpose it to the matrix, and here we had the variables are, we involved only the variables y1, y2, and y3, and that is equal to, here we have considered equal to 48, 21 minus 21, 0, 0. Why? In the cost coefficients in the primal would be the constants, left hand side, right hand side constants in the dual. So these we can represent as 2y1 plus 3y2 plus 17y3, that is equal to 48, and 8y1 plus 4y2 plus 4y3, that is equal to 21, and minus y1 minus 4y2 minus 4y3 is equal to minus 21. I guess here it is 8. 8, right? 2 plus 8 minus 8. And in this, we can say 0 into y1, 0, minus y2, 0 into y3, 0. So that is equal to 0. and minus y3 is equal to 0. Here you consider that it is in the conversion of the given LPP into the dual problem, we are considering minimum into the maximization type. So in the maximization type, all of our constraints should be in less than or equal to sign. So here consider the less than or equal to sign. So from this we can say that the first constraint would be the same. 2y1 plus 3y2 plus 17y3 is less than or equal to 48. And in the second case, here it is minus a, the RHS side is in the negative sign. So to reduce this negative sign, we just convert the multiply the constraint with the minus 1. So if we multiply this with the minus 1, then we can get here it is a greater than or equal to sign. Here one constraint is in less than or equal to sign and other constraint is in greater than or equal to sign. Same. So it would be the equation. Plus 4y2 plus 4y3 is equal to 21. And here you can see that it is minus y2 less than or equal to 0. If we multiply this with minus, then y2 greater than or equal to 0 and y3 greater than or equal to 0. Here we observe that the non-negative conditions for y1, y2, y3 has to get. But we only get that y2 and y3 are greater than or equal to 0. And what about the y1? So in this entire conversion, we didn't get any expression for y1. So you can say that y1 is unrestricted in sign. Here in this case. Is this okay? Okay. Next, move into the next problem. Here is a question that the point, given point that is three-dimensional, 1, 1 and 1 by 2 is a convex linear combination of 1, minus 1, 0, 1, 3 points. These are the another 3 points. So that they are saying that whenever this point is convex linear combination of the given points or a vector, they are asking. How we can say that the convex linear combination means if we consider the points from the any of the set, then let us suppose x1, x2 and x3 are the 3 points that are then we have to show that these are the convex say a convex linear combination. Then we need to say that x1 lambda 1 plus lambda 1 lambda 2 lambda 3 lambda 2 plus x3 lambda 3. Lambda 1 lambda 2 lambda 3 are the another arbitrary variables that are greater than or equal to 0 and 1 maximum. So this gives the whatever the solution we may get that may also involved in the convex set. Then we can say that these points, the combination of the linear convex linear combination is the convex. So they are saying that they had already given the point is a convex linear combination of these points. Let us assume that this is x1, x2 and x3 and this is the convex linear combination they are saying. That means in the RHS side they are already given that 1, 1 and 1 by 2 is the point and x1 is 1 minus 1 0 lambda 1 and 2 0 0 lambda 2 plus 0 4 1 lambda 3. So in this case we need to find lambda 1 lambda 2 and lambda 3. Just convert these into the equations as here you can say that lambda 1 minus lambda 1 0 and 2 lambda 2 0 0 plus 0 4 lambda 3 and lambda 3 is equal to 1 1 1 by 2. Then this means lambda 1 plus 2 lambda 2 is equal to 1 minus lambda 1 plus 0 plus 4 lambda 3 is equal to 1 and 0 plus 0 plus lambda 3 is equal to half. Just solve it and let me know what is lambda 1, lambda 2 and lambda 3. Is everyone aware and following? From the given equations, you can easily tell what is lambda 3. Here, what is lambda 3?
1 by 2, ma'am.
Okay, then after doing substituting this in the first equation or second equation, you may get lambda 1. Okay, sorry. In second equation, you may get lambda 1. What would be the lambda 1?
One ma'am.
Okay, then lambda 2.
0 ma'am.
0, ma'am.
Is everyone getting the same answers?
Yes, ma'am.
So finally, you can say that lambda 3 is equal to half, and substituting it in 2, from 2 you can say that minus lambda 1 plus 4 into half is equal to 1. So that lambda 1 is equal to 2 minus 1, 1. And from the equation 1, lambda 1 is 1 plus 2 lambda 2 is equal to 1. That means lambda 2 is equal to 1 minus 1, 0. Which option he is here involved? Here they given C1, C2, C3. You consider lambda 1, lambda 2, lambda 3. So for the first option, lambda 1 is 1, lambda 2 0 and lambda 3 half. Yeah, this is the right option. So coming to the next question, I just check you how we can do it. Here is the problem related to solving the revised simplex method related example. So first we discuss revised simplex method. Why we use the revised simplex method means sometimes in the simplex method or bigger method or in a bigger method and also in two-phase method, we may get some more calculations and that may becomes wrong sometimes. So that and computer we also solve the given problems in the computer oriented. So computer may also getting to commit with errors. So this revised simplex method means this is only developed because of the computer programming. That means the computer has to store the less amount of memory and gives the efficient results in a faster mode, right? So that to become the lesser calculations had developed the revised simplex method. And the advantage of revised simplex method is with the help of revised simplex method we may get the simplex multipliers or Lagrange multipliers that are the cost coefficients CBs and also the basic matrix inverse. That would be the simplex multipliers, right? Simplex multipliers or Lagrange multipliers. And also these multipliers can be useful in the duality theory and the sensitivity analysis. Why? Because uh, in the duality theory means it may come into the forthcoming weeks how the simplex multipliers can be used in duality theory. I just give you some help that with the help of simplex multipliers, the dual and the primal has the some relation that can we can tell it as strong um, a strong reality in LPP. That will be comes in later. So we can say that the simplex multipliers can be useful in duality theory and as well as in the sensitivity analysis that also comes in the forthcoming weeks. So let's start doing the revised simplex method. What will you do here in the first step? Just solve with me. Try to solve with me. In the first step, we write that the given objective function is in minimization type, so that we just write that maximization of z dash. Z dash is the minus z, minus 20 x1, minus 16 x2, and just we need to convert the given constraints into the equations. Here these are the greater than or equal to sign. So this can be solved by the bigger method or two-phase method. Just assume that by solving with the help of like a big M rule in revised simplex method. So subject to constraints become the equations as 2x1 plus x2 minus surplus variable as let us say that it is s1 and plus artificial variable x1 plus x2 minus s2 plus artificial variable. Here also x1 minus s3 plus a3 is equal to 2.5. And then we assume that in an objective function, uh, uh, the coefficients to the artificial variable as minus m and slack or surplus variable as 0, s1, s2, 0 into s3 minus 0 into s4, and minus m for an artificial variables a1 minus m into a2 minus m a3 minus m a4. Okay. Next, make it in a table. I just come. So to make it in a table, what are the values you obtain? first in the cost coefficient, CV, and then basic variable. What are the basic variables? Here it would be the cost coefficients in the first row. What are the basic variables in our question? Here, what are the basic variables involved in our question?
Ma'am, A1, A2, A3, A4, ma'am. Artificial.
Okay. Uh, so first we write all the variables here. X1, X2, S1, S2, S3, S4. Sorry. X1, X2, S1 to S4. And now the basic variables A1, A2, A3, A4. And the cost coefficients here for X1 minus 20 and minus 16, 0, 0, and minus n, minus n, minus n. And here would be the RHS. 17, 12, 2.5. And now what are the entries here? The basic variables are A1, A2, A3 and A4. And related cost coefficients are minus m. I just write, please let me know what are the entries would be here. Here first, in the first row, the entries are
Ma'am,
okay,
2,
let me
1,
show you.
minus 1.
For x1 2, x2 minus 1 and s1 minus 1 and all remaining are 0, I guess, right? And in next equation, 1. First, please note the given problem and write it in a standard form of LPP. Then we uh, just follow my things. Here 1 1 and x1 0 minus 1 0 0. Sorry. And a1 is 1. And in third equation is x1 and s3. Plus 1. And x2 s4 and a4. If these are the given entries, I made any mistake here. So just identify that the basic variables are A1, A2, A3 and A4. Just make a column separated to the given thing. Here these are all the comes to the A1, A2, A3 and A4. Here we can just simply identify that this is the identity matrix, and these we can say that this is the basic inverse B inverse. This would be the B inverse matrix, and here RHS is also here. And next thing is we have to identify the leaving variable and what is the entering variable. And to identify the leaving variable, we just use the concept of simplex multipliers. So what is the simplex multiplier tells? That simplex multiplier is equal to CB into B inverse. Here our basic matrix inverse is all these identity matrix. And CB means here we observe that CB is minus m, minus m, minus m and minus m. Uh, so just write it here, or you just solve that CB into B inverse. Then you may get a matrix of containing 4 elements. If you do for the first iteration, then it will be the same for every iteration.
Ma'am, we get CB only, no?
CB into B inverse.
हाँ तो B inverse is identity, ma'am. So CB into I identity will be CB only, no?
So you can get the CB only. Yes, of course. What is the CB is minus m, and minus m. So with the help, we just denote this simplex multipliers as pi or any of the symbol you can. So this pi contains the 4 elements, that minus m, and minus m. Now to identify the deviation rows. In general case, we only identify here the deviation rows, that Zj minus Cj or Cj minus Zj. So here we identify the deviation rows as Cj, that is equal to, or we just denote Cj bar, that is equal to Cj minus the simplex multipliers pi into Pj. Here we just say that Pj's are the basic column matrices that are involved in our decision variables, all the column matrices. So here we say that P1 is equal to 2, 1, 1, 1, and P2 is equal to 1, 1, 0, 1, and P3 you can say minus 1, 0, 0, and P4, P5 or P6 here. Up to we had the P4. These deviation rows we just only calculate for the non-basic variables. Here the non-basic variables are x1, x2, s1, s2, s3 and s4. So overall 6 non-basic variables are there. So you need to calculate the Cj bar for C1 bar, C2 bar, C3 bar, and also like that for the 6 variables. I just do for the one. C1 bar is equal to C1. We just say C1 means for the A1, I mean the corresponding Cj, which is minus 20. The cost coefficient related to Pj, and pi means minus m, minus m, minus m. Okay, let me do it down. Here C1 bar is equal to minus 20 minus, it is the matrix minus m, minus m, minus m, row matrix. And Pj is the column matrix. Here Pj means for P1. P1 is 2, 1, 1. Then we get again the row matrix or element. Just do and tell me what is the element here. Element you may get. I was already done, and I guess in my derivations I get minus 20 minus minus 2n minus n 2 1 1 and 0 minus into minus plus. I get this. Is it so?
Yes, ma'am.
So do it the same for C2. C2 means minus 16 minus same minus m this CB, and here PJ only changed as the second column, and let me know.
Ma'am, 3m minus 16, ma'am.
3m minus 16. Okay, 1 2 3. And in the similar way, C3 bar we may get as minus m, and C4 bar is also minus m, and C5 bar is minus m, and C6 bar is also minus m. Please check it. I get those. Is it same to you or not? So out of these you can say that these are the row deviations that is only for the non-basic variables. That means out of these which is has the largest value, that is the corresponding variable becomes the living variable. Sorry, entering variable. Here the maximum value obtained from C2 bar. That means here x2 is okay. Uh, so C2 has the maximum value. So I can say that the cost coefficient which is related to the second column would be the entering variable. This would be entered into the basis x2, and we have to now next thing is to find out the leaving variable. Here the pivotal column is related to x2 only. Here in the general procedure, you can say that this is the pivotal column, the row which is the column which is corresponding to the variable of deviation row which has the maximum value, that is the pivotal column, and we just have to do the minimum ratio test, that as you can say 17 by 1, 12 by 1, and it would be not 6 by 1, and out of this the minimum value we obtained is A4. I guess.
Ma'am, C1 will be entering, no?
Okay, okay, sorry. Here 4m minus 20, so C1 would be the entering variable. Yeah. So whenever C1 is the entering variable, the minimum ratio test becomes the leaving variable would be minimum value at 2.5, right? 2.5 by 1, 17 by 2, 12 by 1. Okay. The minimum value is obtained at A3. So A3 would be the leaving variable and X1 would be the entering variable. So simply with this, we can saying that this is the pivotal column. There is another way to tell the pivotal column. That is, we need to draw an extra table. Uh, that the table considers. Okay, I am showing here only. In the basic table, we had the basic variables are A1, A2, A3, and A4, and the basic matrix inverse is 1 0 0 identity matrix, and we had getting the RHS 17 12 2.5 and 6. These are the RHS values. So here we can do the minimum ratio test. So we can obtain that minimum ratio test as okay, sorry. Here we have to find out the pivotal column, right? So to find out that pivotal column, there is a formula that pivotal column. Here it is C1, right? So P1 bar would be the pivotal column. That would be the B inverse into P1. This becomes the pivotal column. So without doing these all the calculations, we can do the calculation for the pivotal column, and then we can find out the minimum ratio test in every iteration. For suppose in this iteration, we say that P1 bar is the pivotal column, that P1 bar is equal to B inverse into P1, whatever the P1 is. Every time the P1, P2, P3, P4 would not be changed. So B inverse is identity matrix B inverse only, and P1 is 2, 1, 1, 1, 0. So we can easily say that P1 is only the pivotal column. We can we can see the changes in the coming iterations, how the coming iterations pivotal column would change. So from the next steps we can do simply that first we have to calculate the simplex multipliers, and then with the help of simplex multipliers identify whatever the simplex multipliers has the maximum value, and then that would be the entering variable, and to find out the leaving variable we need not to do of the entire calculations here. Only we have to make the basic variables inverse only. So from the next iteration, just do the steps to get the B inverse only. Here the pivotal element would be here 1. So, so in the previous method, what we do is the pivotal element row would be the pivotal element would be 1, and the corresponding column entries should be 0. In that way, we do the row operations. So that after doing these row operations, we can get the B inverse. I mean, than the unit matrix. So after getting this B inverse, with the help of B inverse, just find out the simplex multiplier and the maximum value of simplex multiplier, identify that, so that you can identify the leaving entering variable, and then for the leaving variable just do the calculation separately as a pivotal column entries, and with the help of pivotal column identify the minimum ratio test, and which has the minimum, that would be the leaving variable, and then do it, repeat it again. But here the calculations would be lesser than the previous one. Why? Anyone can guess why we have the lesser calculations in this revised simplex than the other methods, whatever we had learned so far? Okay, let me tell you. Here every time we are calculating the deviation rows for the non-basic variables only. Uh, that means here A1, A2, A3, A4 are the basic variables. So we are just identifying the deviation rows for non-basic variables. Here A3 is entering into the A3 is leaving from the basic variable. So x1 is entering into the basic variable. So in the next iteration, the basic variables are A1, A2, x1, and A4. These are the basic variables, and all other are the non-basic variables. So we just find out the deviation entries for the non-basic variables. So non-basic variables are x2, s1, s2, s3, s4, and also a3. Because a3 is leaving, so it becomes the non-basic variable. But we may not calculate the deviation row entries of A3 because it is an artificial variable, so we are just removing that from the deviation row. And so here we had only the non-basic variables are next time is 4. Initially we had 6 non-basic variables, and then we had 5 non-basic variables, and any of the A1, A2 or A4 is only leaves the basis. X1 should be here only. Uh, so every time we may get the less number of non-basic variables. And next case we only had 4 non-basic variables. And in the next iterations we had 3 non-basic variables. And this would be continuous until we get the no non-artificial, sorry, non-basic variable. Or we coming to conclude when to stop the procedure means here we had the decision variables are x1 and x2. The matrix and basic variables would be sorry, in the last iteration we may get the basic variables related to x1, x2, s1, s2, s3 or s4, and it may not contain the artificial variable. uh, so any of the 4 variables would be coming to the basic variables in the last iteration. So that 4 variables related matrix has the B inverse also. And uh, initially we had the row, sorry, columns that are corresponding to the last iteration variables columns, and just multiply that with the B inverse, then we may get the identity matrix or B. So we can simply say that that is an indication to stop the procedure. So with these repetitions, finally we may get okay. Let me tell. Oh, sorry. Please do and let me know that in the next iteration what is the entering variable and what is the leaving variable. Just do with the simplex multiplier. In the next iteration, I can tell you what would be the B inverse. Why artificial variables have cost m minus m means in the bigger method we assume that artificial variable has the cost minus m. This is the penalty. You can say that penalty method as a bigger method, Charles penalty method. We are doing in the way of big M way.
Ma'am,
Mm-hmm.
ma'am, in this question, ma'am, artificial variable was living in the first iteration, ma'am. So, ma'am, it
Mm-hmm.
let us take that the example that surplus variable or slack variable is leaving the uh, basis. So, in the next step in revise simplex, we will not calculate the deviation of it, ma'am. We will leave out that thing. That like here, ma'am, we have not calculated for A3 in the next iteration. The
Yeah.
sim. So if that it was not an artificial variable, if it was a slack or surplus variable,
Yeah.
so
Then
one
we
should not
have
calculate the next
no,
iteration part of that.
no. We have to calculate that except the artificial variable.
Okay, only in artificial variable we will not calculate the
Yes.
that procedure of deviation.
Yes. Yes. Because we
So
can say that we can get the degenerate solution whenever the basis including the artificial variable. Right.
yes, ma'am.
If the optimal solution contains the artificial variable, then that solution we may say that that is the degenerate solution also. That's why in the revised simplex method we may not get that type of solution.
But ma'am, when there is an artificial, then we say that it is an no feasible solution is there for our problem, ma'am. In the simplex, we say that no, if there is an artificial variable in our table, so we say that okay, it's not an.
It's like a
Feasible solution.
degenerate solution.
Ma'am, there is a little bit confusion between generate, degenerate solution, and what is that, ma'am?
When
Please
the
explain
basic
that.
when the basic solution is involving the artificial variable, then we can say that becomes a degenerate solution. Is
Okay.
it so? Hmm.
But ma'am, it is then infeasible, ma'am, na?
Infeasible?
Ma'am, in simplest table, we say that na, whenever there is the presence of an artificial variable, we say that it is an infeasible solution. The simplest as infeasible solution.
Okay. Then okay. Any of the okay. Okay. So degenerate variable means any of the basic variable has the value 0. Then we can say that is a degenerate. Yes. Yes. Yes.
Deviation row has deviation of a basic is zero, ma'am. That thing or
Yeah. Degenerate solution. Not
okay, ma'am.
deviation.
Base okay. Basic has a zero
Value.
value. Okay, ma'am.
Yeah.
Yes, yes. Got
Uh, then that metal is an infeasible solution. So your question is in revised simplex method, we are not tending to get an infeasible solution, right? Is that
No, ma'am.
your question?
I was asking that. No, I was asking that, ma'am. Ma'am, you have told that revised is much more simpler and much more less time consuming than the previous one because, ma'am, we do
Yeah,
not calculate that
because
for artificial.
in manually we are doing the entire things, but coming to the computer oriented storage, it only stores whatever it requires. That means here B inverse only it can store. It can do the entire calculations, but it can store only B inverse. So with the help of B inverse, we can identifying the deviation rows, and also we are identifying the pivotal column elements. So with the help of pivotal column elements and deviation rows, can easily tell that which is the living variable and which is the entering variable. So it is only for the computer storage thing. Yeah, who raised their hand? Simmons, M. Simmons, you raised the hand. I am not audible to you. Okay, everyone. I asked you in the next iteration what is the living variable and what is an artificial entering variable. Okay, just check that in the next iteration, S3, yeah, S3 is an entering variable and A1 is the living variable. Is everyone got the same in this next iteration? After doing the elementary operations and all this. Okay, time is lagging. Um, I just tell you what is the solution to this given problem in the next. Uh, I'm sharing you another screen. Just wait. Is this screen visible to you all?
Yes, ma'am.
Okay. Here are the questions. Just see whether you are known or unknown. Here is the question that the simplex multipliers are given by anyone or all of you. Please tell.
CB B inverse.
Okay. This is option 3. CB and C B inverse. is the simplex multiplier. And the simplex multipliers are used in duality theory and sensitivity analysis. This will become in the next coming weeks. And here this question we had already discussed that the convex linear combination of some points is already given. So that what is the values of the convex set. We observed that, I guess we solved that A or B in this. And please let me know the answer for 4. If a LPP has multiple solutions, which of the following is true? If we observe in a graphical method that we had a solution involved in this type of triangle. So we are saying that LPP has multiple solutions. Then which of the following is true? The slope of the objective function is same as that one of the constraints, or greater than or less than equal to the other constraints, or it will be the greater than 0. Can say that,
Ma'am, first option.
yeah, it's the first option. Because if we assume that these are the constraint, multiple solutions means all the solutions might involved in these constraint only. So the slope of the objective function is the same as that of the one of the constraints, any of. And which of the following statements is true? In the bigger method, I am also confused about the first option. Just see the 3. The feasible region of an LPP is always a convex set. Is it true or not?
Yes, ma'am.
Yes, that means the optimal solution or feasible solution, whatever you get, that may it be always a convex set. And the feasible domain of the LPP cannot be a single point. It's false. Yes, it's false. And all the subsets of the convex sets are also convex. Yes, it's true, right? All the subsets of a convex set is also a convex set, but here they are given false. So the option is 2 is correct, right? And when a dual is constructed from the primal, then which of the following statement is false? Everyone, please mention your answer here, A, B, and C, in the chat box. Everyone, please type your answer in the chat box. When a dual is constructed from the primal, that means in a dual LPP, which of the following statements is false? The objective function coefficient of the primal becomes right-hand side constraint of the dual. Is it true or false? Or right-hand side constraints of the primal become the cost coefficients of the dual, and the inequalities are reversed in the constraints, and the inequalities become equalities. Which is false? Is the first option is true or false in the dual
No, true, ma'am. First one.
first one is true. Then the second option, the right hand
Mm.
side constants of the primal becomes the coefficients in the dual, right? We just explained in the starting. And the inequalities are reversed in constants. So whatever the inequalities in the primal, that would be the reversed in the dual. And that means the inequalities should not be equalities in the dual problem. So the false option is 4.
Ma'am,
Yeah,
can you explain the third option? Inequality are reversed in the constraints, ma'am.
that means in the constraints of the primal problem is less than or equal to constraints, then in the dual becomes greater than or equal to, right?
Yes, okay, yes.
So, so the inequality greater than or less than or equal to means inequalities. Constraint inequalities are reversed. So it is also the similar type of question. Please let me know. We have to identify the false statement. Everyone, please respond in a chat box. The objective function changes from maximization in primal to minimization in dual. Is it true or false?
True, ma'am.
And then each column in the primal corresponds to a constraint row in the dual. That means the column in the primal constraint becomes a row constraint in the dual. Is it so?
Yes, ma'am.
And then which is the false statement out of these four?
Last option, ma'am.
So there is a no relationship between the objective function values and of the primal and dual objective. Yes, that is false. And if the primal is in the minimization type and here they had given f of y is equal to b transpose y, subject to the constraint a transpose y, it is greater than or equal to c and non-negative restrictions. Then in the dual problem it would be, here it is in minimization type, so in the dual would be maximization type. And the function is has the cost coefficients b's. This primal cost coefficients becomes the constants, RHS constants in the dual. Yes, and the RHS constants would be the cost coefficients in the dual, and here it is an A transpose. So coming to the dual, it would be the transposed form, that is A is so identify which one is true. Here it is less than or equal to 3 means greater than or equal to symbol. Here it is greater than or equal to. So in the given it is greater than or equal to. So coming to the dual, it becomes less than or equal to, right? And minimization, maximization. I think option A is correct. Is everyone guessing the same?
Yes, ma'am.
Okay. Then we just had seen this problem only. So for the revised simplex method, the solution would be D. We can note that and try. And this problem also had covered. So in this week we had done. So is there any doubts in the today's session? If you didn't have any doubts, then just wind up with the today's. Okay, then I'm turning off. Okay, you just come up with your doubts in the next week. I am just turning up the meeting. Bye bye. Good night.